Today, we are diving into one of the most fundamental technologies that allows a machine to actually see and navigate our world. It's how a self-driving car, a warehouse robot, or even your phone's AR system answers two of the most basic questions imaginable. Where am I, and what does this place even look like? The technology that makes it all possible is called SLAM. So let's just think about this for a second. Imagine you put a robot in a room it has never ever seen before. It has no map, no GPS, nothing. How in the world can it build a map of its surroundings while, at the exact same time, it's trying to figure out its own location on that very map it's creating? That, right there, that is the core challenge of SLAM. And that challenge has a name: Simultaneous Localization and Mapping, or SLAM for short. It's famously known as the chicken and egg problem of robotics, right? You need a map to know where you are, but you need to know where you are to build a decent map. Being able to solve both of those things at once, well, that's the magic of SLAM. So to really appreciate just how clever the solution is, we first have to wrap our heads around how big the problem is. Let's take a look at what happens in a world without SLAM. I mean, without this ability, a robot is just lost. It's fundamentally blind and disoriented. It can't plan a path, it can't avoid obstacles, it really can't do any useful autonomous task at all. You can think of SLAM as the foundational sense of digital sight and orientation. It's what enables pretty much every other intelligent action a machine can take. So how does it actually work? Well, SLAM is this continuous feedback loop, a beautiful recursive dance. It starts with the robot's sensors observing the world around it. Those observations are then used to build a first rough draft of the map. Now that slightly better map allows the robot to get a more precise estimate of its own position. And here's the key: that better position estimate then feeds back into making the map even more accurate. Each step just keeps refining the other over and over again. Of course, making that cycle work in the real world, with all its noisy, messy, imperfect data, requires some incredibly clever mathematics. So let's take a look at how engineers actually cracked the SLM code. You know, there isn't just one single way to solve the SLAM problem. Over the years, a few major strategies have popped up, and each one has its own philosophy. Some are probabilistic, meaning they embrace uncertainty from the very beginning. Others focus on identifying distinct features, kind of like landmarks. Some use all the raw sensor data they can get, and others focus on optimizing the entire map all at once. Let's look at a couple of these to really see how they differ. This really illustrates two popular visual methods perfectly. On one hand, you have feature-based SLAM. You could think of this as connecting the dots. The algorithm hunts for really distinct landmarks, like the corner of a table or the edge of a door frame, and it builds a sparse map from those key points. It's really efficient. But on the other hand, you've got direct SLAM, which is more like matching the pixels. It uses all the visual data to build a much denser, more detailed map. The catch? It requires a ton more computing power. But here's the thing. No matter which method you use, there is this persistent, nagging enemy: error. Every single tiny measurement has a little bit of uncertainty. And as a robot moves through a space, these tiny errors start to add up, and they cause the map to drift. A hallway that you know is perfectly straight might start to look like it's bending, and rooms just won't line up correctly. Now, the most elegant solution to this drift problem is something called graph-based SLAM with loop closure. So imagine the robot's path is like a long chain, and with each link a little bit of error gets added. But then the robot has this aha moment. It recognizes a place it's been before. This recognition creates a super powerful connection, or a constraint in the map's graph. And what it does is it allows the algorithm to go all the way back and correct the entire path and map all at once, snapping everything back into place and just poof, eliminating that drift. It's brilliant. Okay, so all these amazing algorithms are great, but they need data, right? Real-world data. So what are the actual eyes and ears that a SLAM system uses to see the world? Let's dig into the hardware. You know, each sensor comes with its own very clear set of trade-offs. Cameras, they're cheap, they give you rich, colorful data, but they're basically useless in the dark or if you point them at a blank wall. Then you have LiDAR, which gives you incredibly precise 3D distance data by shooting out lasers. It's super accurate, but it can be really expensive. And then there are IMUs, which measure motion. They're fantastic for tracking really quick movements, but their accuracy drifts. I mean, it drifts terribly over just a few seconds. And this all leads to a really crucial insight. No single sensor is perfect, not even close. The real robust solution is something called sensor fusion. By intelligently combining the data, a system can use the strengths of one sensor to cancel out the weaknesses of another. So for example, an IMU can track fast motion where a camera would just see a blur, while the camera provides those visual landmarks that correct the IMU's constant drift. They literally make each other better. So we've covered the problem, the algorithms, and the hardware. Now for the really exciting part. Where is SLAM actually being used today? Let's look at its real-world impact because it is everywhere. The most high-profile application is, without a doubt, autonomous vehicles. SLAM is used to create and maintain those incredibly detailed, high-definition maps that self-driving cars rely on. But even more importantly, it's used in real time to get centimeter-level accuracy, figuring out exactly where the car is and its lane, even if it's in a tunnel where the GPS is totally cut out. SLAM is also the core engine of pretty much all modern robotics. It's what allows a warehouse robot to navigate a constantly changing, dynamic space. It's what lets your robotic vacuum efficiently mop your living room. And it is absolutely critical for drones that are inspecting bridges or navigating disaster zones. You know, places where GPS is either totally unavailable or just isn't precise enough. And here's an application that you might not have even thought of: augmented and virtual reality. When you use an AR app on your phone and you place a virtual sofa in your room, it's SLAM that's mapping your room in real time. That's what makes that virtual object stay convincingly anchored in place as you walk around it. It's tracking the real world to perfectly blend it with the virtual. SLAM has already accomplished so much, but the field is far from solved. I mean, researchers are now tackling even bigger and more complex challenges. So let's take a quick look at what's next on the horizon. The next frontiers are huge. You've got researchers trying to scale this technology to map entire cities, and others are trying to master these incredibly dynamic environments like a busy city sidewalk with people everywhere. But maybe the most profound leap forward is what's called semantic mapping. This is about going beyond pure geometry to actually teach a robot what things are. It's the difference between seeing a collection of surfaces and understanding that's a door, that's a chair, and oh, that's a person I should avoid. And that really leaves us with a final, powerful question. What becomes possible when a robot's map isn't just about lines and distances, but about meaning? A machine that can actually understand its environment on a human level could interact with our world in ways we are only just beginning to imagine. And that is the future that SLAM is busy building right now.